Good evening, everyone. Welcome to the problem solving session of NPTEL course on ice engines and gas turbines. I will start with the problem that uh, was that I was trying to do in the last class. So a diesel engine has a compression ratio of 20 and cutoff takes place at 5% of the stroke. Find the air standard efficiency. Assume gamma as 1.4. So first time I will draw the PV plot of the diesel cycle. So the first stroke before suction, the pressure will be low and volume will be high. That is, the piston is at the bottom dead center. Now the air or the working fluid is compressed adiabatically. So it will at the end of the compression, the pressure will be high and volume will be low. So assuming the first state as 1, the second state I am naming it as 2. Now there will be constant pressure combustion, so that means it will be represented as a horizontal line in this PV plot, and then it will undergo an expansion which is isentropic and adiabatic, and then there will be a constant volume expansion. So this is the direction. Now we have this as V1, volume at state 1, volume after combustion is V3. Pandu, if you have some question you can ask. Hello, is the voice low for everyone or is it only for few people?
It's clear, sir.
Sorry?
It is clear, sir.
Okay. Then maybe if someone finds the volume is low, you can try to increase your speaker volume or headphone volume. Now I take volume at the beginning of compression as V1, volume at the end of compression as V2, and volume at the end of combustion, that is after the cutoff, as V3. Now we have been told that the cutoff takes place at 5% of the stroke. So the overall stroke is V1 minus V2, and the cutoff takes place, that is V3 takes place at 5% of stroke. That means V3 minus V2 is 5% of this one. So we have 5 by 100. No, sorry. We have 5% of the stroke as cutoff volume. Now we can calculate the cutoff ratio RC, which is V3 by V2, and here compression ratio or R is given by V1 by V2. From this expression, I will divide everything by V1. First I would take this 20 here, then dividing everything by V1, I will have 1 minus V2 by V1 equal to 20 V3 by V1, or I think it's better I divide everything by V2 because all the ratios have V2 in the denominator. I will have V1 by V2 minus 1 equal to 20 V3 by V2 minus 20. Now I will have R minus 1 equal to 20 RC minus 20. So R plus 19 is equal to 20 RC. We know R is compression ratio is 20, so 39 equal to 20 RC, which implies RC is 39 by 20. So can someone compute RC and tell me? Yes, so 3 is written, it's 1.95. So now we can substitute that in the efficiency formula, which is shown in the right. Here we have 1 minus 1 by r power gamma minus 1 into 1 by gamma into r power rc power gamma minus 1 divided by rc minus 1. In the previous class, this formula was had some problem, so I couldn't solve it properly, so now I got it corrected. So R is 20, power gamma minus 1 is 0.4 into 1 by gamma is 1.4, and we have RC 1.95 power gamma. Okay, I will write gamma as 1.4 minus 1. The denominator I have 1.95 minus 1. So what is eta? What is the value of eta? Has someone solved it? Okay, eta is 0.649, so this is 65% efficiency. So this is for the diesel cycle, air standard cycle. Now assume if we have we see the compression ratio of 20, which is very high when compared to an Otto cycle. We can just compare how Otto cycle efficiency would have been if we have a compression ratio of 20. So that is, for Otto cycle we have 1 minus 1 by r power gamma minus 1, so that is 1 minus 1 by 20 power 0.4. So this is 69.8%. So we see there is a around 5% difference in efficiency between the Otto cycle and diesel cycle for same compression ratio. Do you have any questions with the problem?
No, sir.
determine the ideal efficiency of the diesel cycle having a cylinder with bore 250 mm stroke 375 mm and a clearance volume of 1500 cc with the fuel cutoff occurring at 5% of the stroke. Assume gamma is 1.4 for year. So now bore and stroke of the engine is given and the clearance volume is also given. So for the to compute efficiency we need R and RC value. We have RC, which is we can calculate RC by how we did in the earlier problem, but for as they have given the cutoff occurs at 5% of the stroke, but R value is yet to be found. So R value we know that it is volume stroke volume plus clearance volume divided by clearance volume. Here clearance volume is also given as 1500 cc, but to calculate the stroke volume other parameters like bore and stroke are given. The stroke volume can be computed as a volume of the cylinder, which is pi r square pi by 4 b square stroke, or I will write L. So we have pi by 4. I would since the volume clearance volume is given in cc, it's better to have the lengths in centimeters so that we will get the stroke volume also in centimeters. Now for the bore we have 25 centimeters which is 250 mm and square of it, and then we have stroke as 375 mm which is 37.5 centimeters. Can someone compute this? No one is able to solve this. Okay, so this is 18,408 cc. So now to compute compression ratio, we have Vs plus Vc by Vc, which is 18,408 plus 1500 divided by 1500. So we have 13.27 or 13.3. So we have computed the compression ratio. As we saw earlier, we can calculate the cutoff ratio as it is given that the cutoff occurs at 5% of the entire stroke. So we have the pressure volume curve for the diesel cycle. We have 1, 2, 3, 4. This is V1, cutoff occurs at V3, and the TDC is V2, or the now cutoff occurring V3 minus V2 is 5% of the stroke, that is 5 by 100 into V1 minus V2. So we can do the same thing as we saw in the previous problem. So now finally we will have 39 equal to 20 RC, or we'll have this relation. So that is R plus 19 equal to 20 RC. So we will have compression ratio is 13.3 plus 19 divided by 20. Can anyone solve this? Okay, cutoff ratio is 1.615. Now substituting in the efficiency formula, which is so we have efficiency as 1 minus 1 by compression ratio power gamma minus 1. So one compression ratio is 13.3 power 0.4 into 1 by gamma, which is 1 by 0.4 into cutoff ratio power gamma minus 1. Cutoff ratio is 1.615 power gamma 1.4 minus 1 divided by 1.615 minus 1. So the efficiency is 60.5%. Do you have any questions with this problem? Okay, moving on to the next problem. We have a diesel engine with inlet pressure and temperature at 1 bar and 17 degrees Celsius. Pressure at the end of adiabatic compression is 35 bar. The ratio of expansion, that is after constant pressure heat addition, is 5. So that is ratio of expansion means the volume after the heat addition, before the heat addition is given to be 0.5. And we have to calculate the heat addition, heat rejection and the efficiency of the cycle. So I start by drawing the PV plot for the diesel cycle. So at condition 1, that is the inlet condition, pressure is given as P1 is 1 bar and T1 is 17 degrees Celsius, which is 17 plus 273 290 Kelvin. Pressure at the end of adiabatic compression is 25 bar, that is P2 is 35 bar. The ratio of expansion is given as V3 by V2 is given as 5. Now we have to calculate the heat rejection, heat addition, rejection and efficiency. With the pressure ratio, we can calculate the volume ratio during expansion, during compression. So we have PV power gamma is equal to constant for adiabatic adiabatic compression. So that means P1 V1 power gamma equal to P2 V2 power gamma. Now we know we have to calculate V2 by V1, so that would be P1 by P2 power 1 by gamma.
Second class to
Sorry?
no, sir.
Okay. So now compression ratio is V1 by V2. So taking inverse of this, we will have P2 by P1 power 1 by gamma. That is P2 is 35 and P1 is 1 bar, having 1 by 1.4. So compression ratio is 12.7. Now the ratio of expansion is given. We know the compression ratio, so we can calculate the efficiency. So we have this efficiency formula. Efficiency is equal to 1 minus compression ratio is 12.7 power gamma minus 1, which is 0.4, into 1 by gamma, which is 1 by 1.4, and we have cutoff ratio power gamma minus 1 divided by cutoff ratio minus 1. So we have 45% efficiency. Now we can calculate the heat added to the system. To calculate the heat added, we need the temperature at state 2 and 3. Then we can say Q is equal to Cp delta T, or Cp into T3 minus T2. Now to calculate the temperatures, we have the volume ratio. So the initial temperature T1 is known. Now we have these two relations. During compression, we have P1 V1 power gamma equal to P2 V2 power gamma, and we also know from ideal gas equation PV equal to RT. So that means P1 V1 by T1 is equal to P2 V2 by T2. So now to calculate T2 by T1, we have P2 V2 by P1 V1. We know the relationship between the pressure ratio and the volume ratio. V2 by V1, as we have found here earlier, P2 by P1, and then V2 by V1 is P1 by P2 power 1 by gamma. So we can write this as P2 by P1, P2 by P1 power 1 minus 1 by gamma. So then we will have T2 by T1 is P2 by P1 gamma minus 1 by gamma. So we will have 1 minus 1 by gamma, so that will become gamma minus 1 by gamma. So we know P2 by P1 is 35, so 35 power 0.4 by 1.4 will be the temperature ratio, and we also know that temperature at state 1 is 290. So this is 800.9 Kelvin. So we have calculated the temperature at state 2. Similarly, we need to calculate temperature at state 3. To calculate that, we will again use this, we'll start from this relation. T3 by T2 will be P3 V3 by P2 V2. Now we know the combustion between state 2 and 3 was a constant pressure combustion, so we can cancel these two terms. Now we will be left with only V3 by V2, which is set to be 5. So now we have T3 is equal to 800.9 into 5. So that has become 4004.5 Kelvin. This seems very high, but if the expansion ratio after constant pressure heat addition is 5, then that should be the case. Now we know QH is equal to Cp T3 minus T2. This is 1.004 into 4004.5 minus 800.9. So this is 3216 kilojoule per kilogram. So we didn't calculate or include the mass of the working fluid. So then we will be able to calculate the work done or heat transfer or heat added, heat rejected for 1 kg of the working fluid. If you are given a volume or something at the initial state or at some state, the absolute value of the volume is given, then we will be able to calculate the total mass of the system, and then we can calculate this as absolute terms, heat added, work done. So now, since it is not there, we will calculate everything in terms of per kg, for per kg of working fluid. Now we need to calculate heat rejection. So that is constant volume heat rejection. So we will have Cv into T4 minus T1. So this way I have to calculate the temperature at T4. That means I can, with the volume ratio, I can calculate volume ratio using isentropic expansion correlation, like PV power gamma is equal to constant. I can calculate the temperature at T4 and then calculate. So this is one method, and in the other method we know that the efficiency of the entire system, and we know what is the heat that is added in. So with these two you will be able to find the heat rejected. So I will solve in both the methods. First I will solve using adiabatic expansion by finding the temperature at fourth point. So we know till temperature at 3. Now for temperature at 4 we will make use of this this relation. We had T4 by T3 is equal to P4 V4 by P3 V3. Now we need to calculate. Now we also have P3 V3 power gamma is equal to P4 V4 power gamma. So I don't know the pressure ratio, so I will write everything in terms of volume ratio. So then we will have I have P4 by P3 as V3 by V4 power gamma. So then that becomes T4 by T3 will be V3 by V4 power gamma V4 by V3. This will be V4 by V3 minus gamma V4 by V3. So T4 by T3 is V4 by V3 power 1 minus gamma. Now I have to calculate the volume ratio. I know V1 by V2 is 12.7, and I also know V3 by V2 is 5. Now I need to find V4 by V3. So this is also V1 by V3, because 1 and 4 is a constant volume process between 1 and 4. So we will have the same volume between 1 and 4. So I think Delhi Rajan has raised his hand. So Delhi Rajan sir, can you unmute yourself and ask your question? Okay, if you don't have questions I can continue. With these two things I can write V1 by V2 divided by V3 by V2 will be V1 by V3. So that is 12.7 by 5. So this is 12.54. So now I have got the volume ratio that I should use for the temperature calculation. So this is 2.54 power 1 minus gamma, which is minus 0.4. So T4 will be T3 times of this. So T3 is 4004.5 into 2.54 power minus 0.4. So this is 2758 Kelvin. Now heat rejected is CV T4 minus T1. CV is given as constant volume heat addition is 0.717 kilojoule per kg Kelvin. So we have 0.717 into T4 is 2758 minus T1. In the start of the problem, I think it was given as 290 Kelvin. So this is 1769 kilojoules per kg. So this way we have calculated the heat rejection. Now I said there is another way where we can also calculate, so we would go through that one. So QH is 3216 kilojoule per kg and efficiency is given as 45%. I think we have calculated the efficiency, so that is 45%. Now efficiency, we know that it is useful work done divided by heat input, and work done is also QH minus QR. Now this is 0.45 and QH is 3216 minus QR divided by 3216. With this we can calculate QR. I will have 0.45 times of 3216 as 3216 minus QR. So QR is 3216 into 1 minus 0.45. QR will be 3216 into 0.55. Yes, so that is again 1769 kilojoule per kg. So this is another way by which we can find the QR, and both we see it is matched. Any questions with this problem? Okay, if there are no questions, I'll move on to the next problem. Okay, in this problem, ideal diesel cycle is given. The pressure and temperature as at the inlet are given as 1.03 bar and 27 degrees Celsius. So I would again draw the PV plot. So 1 to 2 is adiabatic compression. State 1 is given, the pressure at 1 is P1 is 1.03 bar and T1 is given as 27 degrees Celsius, which is 300 Kelvin. The maximum pressure in the cycle is 47 bar and the heat supply during, so maximum pressure 43 bar means it is P2, which is also equal to P3 is 47 bar, and the heat supply during the cycle is 545 kilojoules, so that is heat supplied is 545 kilojoule per kg. Determine the compression ratio, the temperature at the end of compression, the temperature at the end of constant pressure combustion, and air standard efficiency. So to calculate the compression ratio, we can make use of the relation between volume and the pressure during adiabatic process. So from here,
This one.
yes. So from this expression, P2 by V1 equal to P1 by P2 power 1 by gamma, I can calculate the compression ratio. So P1 by V2 is equal to P2 by P1 power 1 by gamma. So this is P2 is 47 bar and P1 is 1.03 bar, power 1 by gamma. So I have 1 by 1.4. This is 15.32. So compression ratio, which is V1 by V2, is 15.3. With this, we need a cutoff ratio also to compute the air standard cycle efficiency. Now we know the heat that is applied, so we can now calculate the temperature at the end of compression stroke. So that is T2 by T1. We had the expression already derived somewhere. Yes, so T2 by T1 is P2 by P1 power gamma minus 1 by gamma. This is equal to P2 by P1 power gamma minus 1 by gamma, that is again 47 by 1.03 power 0.4 by 1.4. Now so this is 2.979. We have T2 is equal to T1 into this value. T1 is known as 300 Kelvin into 2.979. So that is 894 Kelvin. Now we have calculated the temperature at state 2. Using the heat addition, we can now calculate the temperature at the end of constant pressure combustion. So we have QH is equal to Cp into T3 minus T2. Now QH is given as 545 and Cp is 1.004. So the QH is also given in kilojoules and Cp is also in kilojoules, so I can use it directly without any conversion. Now T3 is unknown, T2 is 894 Kelvin. So now T3 would be 545 divided by 1.004 plus 894. So this is 1437 Kelvin. So temperature at the end of constant pressure combustion is also computed. now we can calculate the cutoff ratio by using this temperature to volume relation. Now we know from ideal state equation, we know PV equal to RT. Now that is P1, or now we want to compute between 2 and 3. So I would write P2 V2 by T2 is equal to P3 V3 by T3. Now between state 2 and 3 the pressure is same. Now we will have T3, I need to calculate V3, so V3 by V2 is equal to T3 by T2, which is T3 is 1437 and T2 is 894. So the cutoff ratio is V3 by V2, which is what we are computing. So that is 1437 by 894, which is 1.607. Now we have compression ratio and the cutoff ratio. Now we can calculate the efficiency of the diesel cycle. So efficiency I have is 1 minus 1 by compression ratio was given, 15.3. It's here 15.3 power 0.4 into 1 by 1.4 into cutoff ratio power gamma minus 1. So that is 1.607 power gamma is 1.4 minus 1 divided by 1.607 minus 1. This is 62.7%. Do you have any questions with the problem? If there are no questions, I will move on to the next problem. In the next problem, we have a diesel engine that is operating on an air standard diesel cycle which has 6 cylinders of 100 mm bore and 120 mm stroke. The engine speed is 1800 rpm. At the beginning of compression, the pressure and temperature of the air are given. Delhi Rajan, you have raised your hand. If you have any questions, you can unmute yourself and ask, or you can also put in the chat window. Okay, now we have a 6-cylinder engine with a given bore and stroke. The engine speed is 1800 rpm. At the beginning of the compression, the pressure and temperature of the air are given as 1.03 bar and 35 degrees Celsius. If the clearance volume is 1/8 of the stroke volume, calculate the pressure and temperature at the salient points of the cycle. So that means all the 4 points that we see in the diesel cycle. The compression ratio, the efficiency of the cycle, the power output if the air is heated to 1500 degrees Celsius. Okay, again I will start with the diesel cycle. Now P1 is given as 1.03 bar, T1 is 35 degrees Celsius, so this is 308 Kelvin. The bore is given, bore is 100 or 10 centimeter, stroke represented by L is 12 centimeter. The engine speed is N is equal to 1800 rpm. The clearance volume is given as VC is 1/8 of the stroke volume. With this we can calculate the compression ratio. So this means Vs equal to 8 times of Vc. For compression ratio is Vs plus Vc by Vc. So we have 8 Vc plus Vc by Vc. So we will have, cancelling all the V, we will have compression ratio as 9. The efficiency of the cycle. Okay. Now we can start calculating the pressure temperature at each points. So P1, T1 is known. To calculate P2 we need the compression ratio, so that is given. We have P1 V1 power gamma is equal to P2 V2 power gamma. To calculate P2 we have P1 V1 by V2 power gamma. So P1 is 1.03 bar, V1 by V2 is 9 power gamma is 1.4. So we have 22.3 bar at the end of compression stroke. Now we also know P1 V1 by T1 equal to P2 V2 by T2. So T2 is P1 V1 by P2 V2 into T1. P1 is known, sorry, it is P2 V2 by P1 V1. P2 is 22.3 bar and P1 is 1.03 bar. V2 by V1 is inverse of compression ratio, so that is 1/9 into T1 is 308 Kelvin. So this is 741 Kelvin. So this is a temperature pressure at the end of compression stroke. We have told that the air is heated to 1500 degrees Celsius. So T3 is given as 1500 degrees Celsius, which is 1773 Kelvin. now now I can calculate the pressure at point 3. Okay, sorry, pressure at point 3 is same as pressure at point 2, but anyway, then now I need to calculate the volume ratio, that is V3 by V2, which is cutoff ratio, so that we can calculate the efficiency later, and also yeah, I think it will help in calculating the efficiency. Now between 2 and 3, if I write the equation, ideal gas equation, I would have P2 V2 by T2 equal to P3 V3 by T3. To calculate T3, I have P3 V3 by P2 V2 into T2. So I know T3 is 1773, divided by T2 is 741. So P2 and P3 and P2 are same, because it is a constant pressure heat addition. What I am left with is V3 by V2. So this is cutoff ratio. This is 2.39. So I know that compression ratio is 9 and cutoff ratio is 2.39. I can compute efficiency, which is 1 minus 1 by R is 9 power 0.4 into 1 by 1.4 into cutoff ratio power gamma, which is 1.39 power 0.4 minus 1 power 1.4 minus 1, and then in the denominator I have 2.39 minus 1. This is 49.1% efficiency. So I've calculated the efficiency. Now I have to calculate the pressure and temperature at the fourth point. For this I have pressure known at the third point, pressure and temperature known at third point, and I also have the volume ratio. Based on volume ratio, I know P4. I am writing from this relation. P3 V3 power gamma equal to P4 V4 power gamma. This is P4 is equal to, we will have P3 V3 by V4 power gamma. So here V4 is V1. To compute V3 by V1, we know from this R is V1 by V2, and this RC is V3 by V1. Sorry, V3 by V2. V3 by V1 is R by RC, right? That is 9 by 2.39. which is 3.76. Now I know pressure at third state is so pressure at second state and third state are equal, so which is 22.3 bar. So I will have 22.3 into this V3 by V1, which is 3.76 power gamma. I think this would be V1 by V3, right? Because R is V1 by V2 and then RC is V3 by V2. Cancelling the V2, we will have V1 by V3. So that means V3 by V1 is 1 by 3.76. I would have 1 by 3.76 power gamma, which is 1.4. So this is 3.49 bar. Similarly, temperature at V4 can be at fourth position can be calculated. We have P3 V3 by T3 is equal to P4 V4 by T4. We know P3 is 22.3 bar into V3 by V4 equal to P4 by P3. So we have P4 as 3.49 and then I have T3 here. I think it is confusing. I will write it the values directly. So P3 is 22.3 into V3 I have as it is. T3 is 1773 Kelvin equal to P4 is 3.49 bar into V4 divided by T4. So T4 is what we have to calculate. We have 3.49. So this 3.49 into 1773 divided by 22.3 into V1 by V3. You know V1 by V3 is 3.76. So this is 1043.3 Kelvin. So I have calculated the pressure temperature at all states and the compression ratio is also calculated. I have calculated the efficiency. Now the power output has to be calculated. For power output we can compute QH and so work done is equal to heat input into efficiency. Now heat input is Cp T3 minus T2 into efficiency. Cp is 1.004, T3 is 1773 Kelvin and T2 is 741 into efficiency is 49%, so that is 0.491. So this is 508.74 kilojoule per kg. In this problem we can calculate the work done per unit mass of the working fluid, but the original bore stroke of the engine is given, and also the intake pressure temperature conditions are given. So with this we can calculate the mass of the working fluid that was present at the start of the stroke. So to if we calculate that, we instead of telling work done per cycle per kg in terms of per kg, we can also tell directly work done per cycle. So I would calculate the volume at 1, or I will calculate the stroke volume by pi by 4 into, I have 100 mm bore and 120 mm stroke, so that is 0.1 square into 0.12. I am writing everything in meters so that I can directly have density and get it in terms of kg. So this is 9.42 into 10 power minus 4 meter cube. This volume, stroke volume, with PV is equal to MRT. We can calculate rho as M by V, so that will be M by V is P by RT from this relation. So density is P by RT, pressure is given as 1.03 bar, bar to convert into SI units we have 10 power 5, and R is 287. Initial temperature was given as 308 Kelvin. So this can be computed. So this is 1.165 kilogram per meter cube. This is the density of air that is inside the cylinder. We know stroke volume is 9.42 into 10 power minus 4. 9.42 into 10 power minus 4 meter cube. So mass in one cycle of the engine can be computed as rho into Vs. So this is 1.165 into 9.42 into 10 power minus 4. So M cycle is 1.097 into 10 power minus 3 kilogram. So this is a mass, or this can be written as 1.1 gram. So 1.1 grams of air was inside the is sucked by the cylinder for every cycle, and since we know that work done per cycle is around 508.74, we can calculate what is the total work done per cycle. So work done is 508.74 into 1.097 into 10 power minus 3. So this 508 was in kilojoule per kg, and now this fluid mass is in kg, so finally we will get in kilojoules. So this is 0.558 kilojoules. So this is 558 joules per cycle. We have to calculate the power output. So that will be in joules per second, right? We are told that the speed of the engine is 1800 rpm. It is not given if it is a 4-stroke engine or a 2-stroke engine, but we will assume it as a 4-stroke engine. So that means it will have 1800 by 60 rps or 1800. So that means for every 2 revolutions we will have 1 engine cycle. So I am dividing revolutions per second by 2 to get cycles per second. So this would be 15 cycles per second. We have calculated that for every cycle we are getting 558 joules, but there are 15 cycles happening at 1 second. So we can calculate power output as 558 into 15. That is 8370 joules per second. So this is 8.37 kilowatt. Is that the power output? Actually, we were told that we have a 6-cylinder engine. So that means we have calculated the so far per cylinder. Now we have to multiply for 6 to get the power output for 6 cylinders. So these are per cylinder. Right? So power output of the engine is 6 into, which is where 6 is the number of cylinders, into 8.37. That is 50.22 kilowatt. So have you understood the problem? Or if you have any questions, we can clear it now. Okay, if there are no questions, I can move on to the next problem. Now so far we have dealt with the Otto cycle and diesel cycle. Now I would start up on the carburetor system. I think you would have, if you have attended the class, assume, yeah. So this is the intake manifold. There will be throat here. So at this throat, the area is very less. That means the pressure at throat will be, I put this as 2 and this as 1. Pressure at 2 will be less than pressure at 1, but velocity at 2 will be greater than velocity at 1. And to supply fuel to the engine, there will be a fuel float. Which will have fuel at this level, and this will be at 1 atmosphere, P ambient. when since the pressure of the air at the throat is lesser, that is at P2 is low, the fuel will start flowing from this tank surface to the intake stream. So that is how we get fuel for the in case of an SI engine, and this process is called carburation. And this is a kind of simple jet carburetor. And once the fuel starts flowing through the throat, on the way it goes inside the cylinder, the fuel and air get mixed, and then we will have a pre-mixed combustion in the SI engine. So now the mass flow rate of the fuel depends upon the throat area and also the pressure differences between atmosphere and the pressure at the throat conditions. And this is chosen correctly to decide the air-fuel ratio of the mixture. Now we see a simple jet carburetor which is required to supply 5 kg of air and 0.5 kg of fuel per minute. So that is m dot A is 5 by 60 kilogram per second, and similarly m dot F is 0.5 by 60 kilogram per second. The specific gravity of the fuel is 0.75, that means density is 750 kg per meter cube. The air is initially at 1 bar, so P1 is 1 bar and T1 is 300 Kelvin. Calculate the throat diameter of the choke for a flow velocity of 100 meter per second. So that means at throat the velocity V2 has to be 100 meter per second. The velocity coefficient is given as 0.85, so CV is 0.8. If the pressure drop across the fuel metering orifice is 0.8 times that of the choke, so pressure difference across the fuel metering orifice is 0.8 times the pressure difference across the choke, that is for the air stream. Calculate the orifice diameter, assuming CDF is 0.60 and gamma is 1.4. Now assuming steady flow, the enthalpy or the energy at 1 and energy at 2 should be same, because there is no heat transfer or there is no work transfer to the system. That means if a kinetic energy can be converted to enthalpy, or enthalpy can be converted to kinetic energy. So here enthalpy is converted to kinetic energy at throat 2 because the velocity gets increasing, and when we compare the velocity at through, the velocity at 1 is very low, so we assume that the velocity at 1 is almost 0, and then we will get the expression like this. So to calculate at velocity at 2, C2 is Vc So we will get this expression when we solve the steady flow energy equation. Here Vc is the coefficient of velocity coefficient. Now with this we can calculate the pressure ratio P2 by P1, and then we can calculate the pressure at throat. C2 is 100, Vc is 0.8, and then we have Cp as 1.00. We can write it directly in SI units. So Cp is 1004 joule per kg Kelvin, and T1 is 300 Kelvin, 1 minus P2 by P1, 0.4 by 1.4. With this we can calculate P2 by P1. So if we take 0.8 to this side and take square, we will have 2 into 1004 into 300 minus 1 minus P2 by P1, 0.4 by 1.4 equal to 100 by 0.8 the whole square. This is 1005,625. I'm taking these numbers to the other side. This is 0.0259. Now I have P2 by P1 power 0.4 by 1.4 is equal to 1 minus 0.0259. That is 0.974. P2 by P1 is 0.974 power 1.4 by 0.4. This is 0.912. We know pressure at state 1 is 1 bar, so that means P2 is 0.912 bar. So we have to calculate the throat diameter. For this we need the density at state 2, which is P2 by to calculate density at state 2 we need P2 by we need pressure and temperature, so that is P2 by RT2. We know pressure at state 2, but we have to calculate the temperature. We know P1 V1 power gamma is equal to P2 V2 power gamma. That is at state 1. I think we didn't calculate the density, right? Assuming rho 1 is P1 by RT1, which is 10 power 5 by 287 into 300. This is 1.16 bar, 1.16 kg per meter cube. In terms of V1 is 1 by rho 1, which is 0.861 meter cube per kg. Now using this relation, we know P1 is 1 into V1 power gamma is 0.861 power gamma or 1.4 equal to P2 is 0.912 bar into V2 power 1.4. V2 is 1 by 0.918 power 1 by gamma of 1.4 into 0.912. So this is 0.969 meter cube per kg. So density at state 2 is 1 by volume, specific volume. This is 1 by 0.969. So we have 1.032 kg per meter. We know mass flow rate is rho into A into velocity. At throat, we know the condition, density is 1.032 and into area is pi by 4 into throat area, which is D. I would write as D square, D as a throat diameter, and velocity is known as 100. And we know m dot air was given as 50 kg per minute, so that is 50 by 60 kilogram per seconds. Sorry, it is 5 by 60. Yeah, so now we have diameter as 60 into, we have 5 into 4 divided by 1.032 into 100 and root of this. So this is 0.44 meters. Sorry, I think I missed the pi by 4. So pi will be I'm getting a high value. This doesn't seem to be right. Has someone found a problem with this? We have d square is 60, sorry, we have 5 into 4 by 60 into 1 by 1.032 into 100 into 5. I think I missed a 60 last time. So this is 1.028 into 10 power minus 3. So that means 0.032 meters. So that is 32 mm. 32 mm should be the throat area to get this air flow rate. Now we have told that delta pressure in the fuel circuit is 0.8 times the delta pressure in the air circuit. Delta pressure in air circuit is given to us, yes, so that we have calculated. So pressure pressure before the throat at this ambient is 1 bar, and pressure at the throat is 0.1912 bar. So we have 1 minus 0.912. So this will be 0.0704 bar. Now for the flow rate of fuel m dot f, we have under root 2 delta p by rho f. Sorry, I think this will be the velocity of the fuel. Yes, so this is 2 into rho of 0.0704. Writing in SI units, I have 10 power 5, and density of the fuel is given. That is specific gravity is 0.75, so we have calculated this 750. This is 4.33 meter per second. M dot F is equal to, we have 0.5 by 60, so this should be equal to rho into area into velocity of the fuel. So that is 0.5 by 60 is 750 into pi by 4 d square into velocity is 0.33. So we have d square. So this is, I would say, throat diameter, and this is orifice diameter, DO. This is 0.5 into 4 divided by 60 into 750 pi into 4.33. This is 1.807 into 10 power minus 3 meters. So that means the orifice diameter should be around 1.81 mm. Do you have any questions so far? Please let me know if you have any questions. I just want to know if you have seen this the derivations or this formula during the coursework, during the video, and you have understood it earlier, or you haven't seen the videos at all, or how is it? Can you write in the chat box, or you can unmute and talk to me? Okay, seems like no one is ready to. Okay, I will go to the next problem. The air-fuel ratio in an aeroplane engine gone through derivations. Okay. Okay, Ram. So also, which year you are in? I hope you are in mechanical undergraduation, right? You are in second year, third year, or
Yeah, mechanical undergraduate. So
yeah, which year?
I think second year.
Second year. Okay. Then that means you haven't seen these classes or the contents in your university so far, but this is the first time you are seeing in NPTEL, right?
Uh, yeah, these detailed derivations I've not gone through. Yeah, but this time what I'm looking at. Yeah,
Okay,
first
okay,
time.
okay. Good to know. Okay. The next problem, we have to determine the change of air fuel ratio in an aeroplane engine carburetor when it takes off from sea level to a height of 5000 meters. The carburetor is adjusted for 15:1 ratio at sea level, where air temperature is 27 degrees Celsius and pressure is 1 bar. The assume the variation of the temperature of air with altitude at T equal to Ts minus 0.0065 H, where H is in meters and T is in degrees Celsius. So T1, I would write this temperature at sea level as TSL, which is 27 degrees Celsius or 300 Kelvin, and P1 is 1 bar, or okay, this is P at sea level. Now to compute the temperature at an altitude, relation is given, and similarly air pressure decreases with altitude as per the relation H is equal to 19200 log 1 by P base 10, where P is in bar, and evaluate the variation of air fuel ratio with respect to altitude in steps of 1000 meters on the trend. So we have pressure and this at state at sea level. To calculate the temperature at a height, assume we will take a height of 5000 meters initially. Then we have T at altitude is equal to T as at S minus 0.0065 into H. Then we have 300 Kelvin minus 0.0065 into 5000. So temperature at an altitude is 267.5 Kelvin. And similarly for the pressure, we have H as H is equal to 19200 log of 1 by P base 10, right? So we have 5000 here. Yes, log of 1 by P base 10. Now P is in bar. Okay, so P is what we have to calculate. So this 5000 by 190, this is 0.2604. Taking log, anti-log, we will have 1 by P is equal to 10 power 0.2604. This is 1.821, which means this is 0.549 bar. You can calculate rho at sea level, which is P by RT, that is 10 power 5 divided by 287 into temperature is 300 Kelvin. Similarly, rho at altitude is same P by RT, where P is 0.549 into 10 power 5 divided by 287 into temperature at altitude, which is 267.5. This is 1.161 kg per meter cube. This is 0.715 kg per meter cube. Now we have computed the density at different altitudes, or at the ground and at an altitude of 5000 meters. Now we can calculate the airfoil ratio. We have P at sea level as 1.165 and P at altitude as 0.715. This is 1. From earlier derivations, you would have got to know that airfoil ratio is proportional to the square of density. So that means airfoil ratio at sea level by airfoil ratio at altitude is equal to density at sea level by density at altitude. So we can calculate airfoil ratio at altitude as airfoil ratio sea level into density at altitude and divided by density at steady at sea level. Now we know this airfoil ratio at sea level is 15 and density at altitude is 0.715 and divided by density of at sea level is 1.161. This is 9.24. So when the aircraft goes to a higher altitude, the airfoil ratio reduces. That means the mixture gets richer because the air density gets lower. Similarly, we are being asked to calculate the airfoil ratio at different altitudes at 0 in steps of 1000. So we know at this one at ground state it is 15 and at an altitude of 5000 it is 9.24. We can fill the other things using all the relation. We cannot directly take an interpolation because, as we know, the temperature Temperature is linearly varying, but pressure doesn't vary linearly. It has some log terms in it, so we cannot take a direct interpolation and fill this table. Any questions in the problem?
No, sir.
Okay. Now I will move on to the next problem. In this problem, a 4-cylinder 4-stroke diesel engine is given, which develops 100 kilowatt at 3500 rpm. The brake specific fuel consumption is 180 grams per kilowatt hour. Calculate the quantity of fuel to be injected per cycle per cylinder. Specific gravity of the fuel may be taken as 0.88. Now it's a 4-cylinder engine. It is a 4-cylinder engine. The total power is 100 kilowatt. That means power per cylinder equal to 100 by 4, which is 25 kilowatt. That means it is 25 into 10 power 3 joules per second. Using speed, which is 3500 rpm, we know, and it is a 4-stroke engine. So that means for every 2 revolutions there will be 1 cycle, and we can write this as 3500 per by 60 revolutions per second, or 3500 by 2 into 60 cycles per second. This is 29.17 cycles per second. Now we can calculate energy per cycle. That is, we are getting 25 into 10 power 3 joules per cycle per second, and there is 29.17 cycles per second. So striking this out, we will get joules per cycle. This is 857.04 joules per cycle. So this is the energy output. So this is the mechanical energy output, and to know how much fuel that is getting consumed, we have some term called BSFC, which is brake specific fuel consumption. That states that we need 180 grams of fuel for every kilowatt hour of energy that has to be produced. Now using these two, like energy per cycle and the BSFC, we can calculate what is the grams of fuel that has to be given into the cylinder for every cycle. Now I want to so this is in terms of 180. So we know we need 180 grams for every kilowatt hour, but it would be easy for us to calculate if we know how many grams of fuel is needed to produce every joules of energy. So we have to convert this kilowatt hour to joules. So 1 kilowatt hour means 1000 watt-hour, or it is joule per second into hour, right? So we will have 1000 joule per second into 3600 seconds. So this way we will have 3.6 into 10 power 6 joules. So 1 kilowatt hour represents 3.6 into 10 power 6 joules. Now with BESFC, we know it is 180 grams per kilowatt hour, that is 180 divided by 3.6 into 10 power 6 joules, right? Now we will get grams per joules. So this is 5 into 10 power 5, 10 power minus 5 grams of fuel is needed to produce every joule of mechanical energy output. We know the energy per cycle is 857, so that means the fuel mass per cycle is 857.04 into 5 into 10 power minus 5 grams. This is 0.0428 grams of fuel is needed for every cycle. Now we need to calculate the volume. It is given the specific gravity is 0.88, so that means specific gravity is 0.88. That is density of fuel is also 0.88 gram per cc, and we know energy requirement is not the energy requirement, the mass of fuel is 0.0428. grams per cycle. To calculate the volume of fuel that is needed, we have mass of fuel into mass of fuel divided by density of fuel, which is 0.0428 divided by 0.88. This is 0.0486 cc per cycle. So that means we need to inject 0.0486 cc of fuel, of diesel fuel, into the cylinder to generate 100 kilowatt of power at 3500 rpm. Any questions in this problem? Okay, this is the last problem. We have a 6-cylinder engine, 6-cylinder 4-stroke diesel engine, which develops a power of 200 kilowatt at 2000 rpm. The BSFC is given as 0.2 kilogram per kilowatt hour. At the beginning of injection, the pressure is 35 bar and the maximum cylinder pressure is 55 bar. The injection is expected to be at 180 bar and maximum pressure at the injector is set to be at about 520 bar. Assuming the following conditions: CD for injector, specific gravity of fuel, atmospheric pressure, and effective pressure difference is equal to average pressure difference over the injection period. Determine the total orifice area required per injector if the injection takes place over 16 crank angles. The orifice, okay, so this is the answer. We can start solving the problem by calculating the quantity of fuel needed for every cycle, like in the previous case. Now we have power, total power as 200 kilowatt, but power per cylinder will be 200 by 6 equal to 33.3 kilowatt. So this is happening at 2000 rpm, which means it is 2000 by 120 cycles per second. So that is 16.67 cycles per second. This is into 10 power 3 joules per second. So we can calculate energy per cycle is 33.3 into 10 power 3 divided by 16.67. This is 1997.6 joules per cycle. And BSFC is given as 0.2 kg per kilowatt hour, which is 0.2 kg, or I would write 200 grams for 3.6 into 10 power 6 joules of energy output. And our energy, we need only around 1997.6 joules per cycle. That means mass of fuel per cycle will be 200 divided by 3.6 into 10 power 6 into 1997.6. So this is 0.1109. So we need 0.11 grams of fuel for every cycle. We need to calculate the orifice area, and this m dot f is given as rho into area into velocity, whereas velocity is given as 2 delta p by rho. So to calculate delta p, it is given as the effective pressure difference is average pressure difference over injection period. So the injection happens till the point where the diesel engine has a peak pressure. So that means the maximum cylinder pressure goes to 55 bar. Okay, the beginning of injection is 35 bar and maximum cylinder pressure is 55 bar, and the maximum pressure at the injector is said to be 520 bar. That means initially the pressure difference is 180 minus 35, right? Because initially the injection happens at 180 bar, and pressure at the beginning of injection is 35 bar. That is pressure of the cylinder at beginning of injection is 35 bar, and during the end of the injection we have the pressure difference to be 520 bar minus 55 bar. and we have been told that the effective pressure difference is the average pressure difference over the entire injection duration. So I'm just adding these two and dividing by 2 to get the average pressure difference. So this would be the effective pressure difference. This is 305 bar. So plugging this into the velocity relation, we have 2 into 305 into 10 power 5 divided by the density. Density is specific gravity is given as 0.85, so this is means 850 kilogram per meter cube. So I would write 850 here, and I can calculate the velocity. So velocity is 268 meter per second, and we have m dot f. M dot f is rho a v, and discharge coefficient is given, so you would write the equation with the discharge coefficient. Discharge coefficient is CD of the injector is 0.75, so this is 0.75 into density of the fluid is 850. For area we have pi by 4 d square, where d is the injector orifice diameter, and velocity of the fluid is known, 268. Now on the left hand side we have m dot f, whereas the total mass is known, but the time taken for the injection is not yet calculated. The time taken for injection can be obtained from using this detail, this data, that is, it takes place over 16 crank angles, and the engine rotates at 2000 rpm. So 2000 rpm means there will be 2000 into 360 crank angles per minute, or we can write 2000 into 360 by 60 crank angles per second. So in principle we can write it as 6n crank angles per second. So if you write this as 6n rpm, there will be 6n crank angles per second. So here it is 12,000 crank angles per second, and it is given as the delta theta is 16-degree crank angle. So the time taken for 16 crank angle will be, delta t will be delta, directly write, it is 16 by 12,000. So that is 1.33 into 10 power minus 3 seconds. So this is 1.33 millisecond. So this means the injection happens at a very small span of 1.33 milliseconds. Now we know, using this, putting this expression, we have m dot f by t on the left hand side, mf by t. Mf we have calculated it as 0.11 gram per cycle. So having this in SI units, I have into 10 power minus 3, so the mass will become kilogram, and in the denominator I have 1.33 into 10 power minus 3, again to be in SI units, and on the right hand side I have few numbers. I would write something into d square. So this is 134185 into d square. On the left hand side we had 10 power minus 3 getting cancelled out, and d square is 0.111 by 1.33 into 134185. This is 6.22 into 10 power minus 7, or taking square root of it, I have 7.89 into 10 power minus 4 meters. So this is 0.789 mm, right? Which is 789 micrometer. So this is the diameter of the injector orifice to get this power output when the PSFC is given as 0.2 kilogram per kilowatt hour. You have any questions with the problem? If there are no questions, I think we can close the session. It's already 7 minutes over time. Okay. Thank you for attending. We'll see.
Thank you, sir.
Yeah, we'll see in the next session. Thank you.